So right now we're going to talk about energy. This right here is the only definition of energy we are going to accept. Energy is the integral of F dot dr. That is our math definition of energy. And we're not going to be giving a typical English written definition. Because this right here is how we're going to identify how energy is stored within a system, how energy is transferred into or out of a system, and really what energy does once it is within a system. This is the definition we're going to be working with, and it is an inherently calculus-based definition. We're going to try to break it down into an algebraic approximation of the calculus definition, but it will be hard to divorce ourselves entirely of the calculus definition of energy, which is why it is of the utmost importance to remember how it is written and what it means. Capital E is the symbol we use for energy. These three horizontal lines is a math symbol meaning is identical to. This symbol is the integral of, and it just is another way of saying the area under the curve of a force versus position graph. Now the R is the symbol that we're going to be using for position. You might see it as D for distance, X, Y, or even Z as the X, Y, or Z positions, but a very traditional approach is to leave it as the letter R for position. The dot here is very deliberately stated. The dot means this is a dot product. Basically, it's going to be a calculus operation where you take two vector quantities, in this case force and position, multiply them together, and then you will end up with a scalar quantity. The big thing with our dot products is that those two vectors will need to be multiplied where they are parallel in direction. Now we're going to start off with a very straightforward force versus position graph, where we have a constant force at every single position. We're still using that exact same definition of energy. Energy is the integral of F dot dr, where energy is the area under the curve of a force versus distance graph. However, the reason why we're starting off with this one is this is a type of graph that we will occasionally see. A horizontal line on a force versus position graph. While we could definitely use calculus and integrate F dot dr, we can also see that the area under the curve here is a rectangle, so we can solve this using geometry. So solving for this shaded area would be a way for us to calculate the energy that we have in our system here. Energy would be equal to the area under the curve on a force versus position graph. The area of a rectangle is the base times the height. So our energy here would be equal to force times the position. Or really, it would be the change in position, so force times displacement. This is a common shape that we will see in an algebra-based physics class. We would also be exposed to this shape for a force versus position graph. We might see a directly proportional relationship. Energy is still the area under the curve of a force versus distance graph. Energy is the integral of F dot dr, and we can solve for this using calculus. Or once again, geometry could be a way to solve for this. The area under the curve on this graph is a triangle. The area of a triangle can be calculated as 1/2 base times height. So our energy here would be 1/2 times our force times our displacement. We can even extend this to when we have a linear relationship. Energy is the integral of F dot dr. We can integrate this, or we can solve it using geometry. We can break this up into two shapes, a triangle and a rectangle, and then add those two areas together, or we can use an equation for that of a trapezoid. By the way, we have two geometric approaches to solving for the area under this curve. All of those geometric approaches are very useful when we have discrete shapes for the area under the curve. That is not always going to be the case. Occasionally we are going to see a varying force, and this is where the calculus will be necessary. But we can still approximate that area just using geometry. The easiest shape for us to geometrically solve for is a rectangle. So we can just place a bunch of rectangles under the curve. and trying to scale the height of them up to match the shape of the curve. So, and then we would just calculate the area of each of those individual shapes, force times the displacement. And then we would just add up all of those shapes. But one thing that we can see here is there's going to be some areas that we overshoot, the area under the curve, or undershoot. So this change in position for each of these bases of these rectangles is a bit too wide for us to accurately approximate the area under the curve here. But if we make them smaller, we do a better job of approximating the area under that curve. Make them even smaller and we do an even better job. Eventually, we do such a good job, and the width of each of those bases is so infinitesimally small. We're basically limiting that change in position to 0. And then when we do that, if we still add up all of the force times change in positions, those areas of each rectangle, that's really going to be our definition of the integral of f dot dr. As we get more and more advanced in our math classes, we're going to have more and more strategies for actually solving for this using calculus. But until we do, we can be focusing on geometric approximations, because that's really all an integral is going to be. The area under the curve, and a traditional way of solving for that would have been adding up those individual areas. And it'll still work for us for the majority of this class. Now let's return to our original graph shape, that horizontal line on a force versus position graph. This is where we can introduce this definition of work. Work is going to be equal to force dot x. At this point, I'm returning to our traditional x-axis position variable, for the simple reason that when I write it like this, a traditional approach will be fx cosine theta. And I want to make it explicitly clear why this is a very traditional way of writing our definition of work. If we go back to our original explanation of what a dot product was, those two vector quantities needed to be parallel to each other. However, we've seen with quite a few force diagrams that the original force we have is not always going to be parallel to the displacement. So if we have this original force here, and this object is displaced in an x-axis direction, the entirety of this force would not be causing that displacement. So we would need to solve for the horizontal, or the x-axis component of the force. So if this is where the angle is, fx over the original force is equal to cosine theta. And when we rearrange that, we can say that our force times our cosine theta is equal to fx. So really, what we're saying here, it's f sub x times our x, or our displacement, is our work. But this is a very traditional approach. You'll see this a lot in textbooks, other videos, maybe even some test questions, where you have fx cosine theta, fd cosine theta, fr cosine theta, whatever variables that they're using for position. And then that just comes from when we have a constant area under the curve for a constant force versus position graph. Of course, we can go back and apply those previous examples of the area under the curve for those different force versus position graphs to figure out different work definitions, but this is great for a constant work, a constant force that is applied over a displacement. Now, work is going to be energy. But what it specifically is, it is the energy that is transferred into or out of a system. By convention, work is considered positive when energy is transferred into the system, and it is considered negative if that energy is transferred out of the system. This is the equation that we'll typically be using. Work is going to be equal to F dot x. Once again, a common way of seeing that is Fx cosine theta. The way that I'll typically be writing this, though, is like this. Work is equal to F sub x times x. Because we're not always going to be given theta. the angle between our original force and the horizontal plane. We've seen quite often that a lot of times we're given the angle between our original force and the vertical plane. And then just writing it like this helps us to avoid that mindless plug and chug approach to some of these problems and makes us really pause and figure out how do we solve for F sub x in order to determine how much energy was transferred into the system via work. Once energy enters the system via working, it can be stored in the system and be stored in several different accounts. One such way is our elastic energy account. Elastic energy is the energy that is stored within a system that causes a material to be stretched or compressed and be allowed to be returned to its original state when energy exits the system once again or gets transferred to another energy account. On a force versus position graph for our elastic energy, the force would be the restoring force of the spring, and then our x is going to be the displacement. We saw that our restoring force of the spring was directly proportional to our position, or rather the displacement. And we ended up with this equation here. Our restoring force of the spring was equal to our spring constant times the displacement. And then we actually included a negative sign there because the displacement would be in the opposite direction of the restoring force. But we're just going to leave it like this while we're determining an equation for the elastic energy. Our elastic energy is the energy stored within the system. It is the energy that is the integral of f dot dr, the area under the curve on this graph. Well, we certainly can solve for it once again with calculus, integration. This is a triangle. We can solve for it using geometry. So our elastic energy is equal to the area under the curve on this graph, which is 1/2 base times height. So our elastic energy equals to 1/2 times our displacement, or the position, which is our base, times our height, which is our restoring force here. We can rewrite this where instead of force, we write it as kx, that spring constant, times the displacement. And then we just combine like terms. It'll be elastic energy is equal to 1/2 kx squared. This is a way for us to solve for the elastic energy stored within a system if we know the spring constant and the displacement. We can solve for that exact same equation by actually using an integral. So our elastic energy is the integral of the restoring force of the spring dx. Now, you might notice that the dot product is removed from this equation. And that's really just because our restoring force of the spring is in the exact same axis as our displacement. So the dot product would be the equivalent of a multiplication operation here. Our restoring force of the spring is kx, so elastic energy is equal to the integral of kx dx. When we solve for that, it's 1/2 kx squared is equal to our elastic energy. The exact same equation, solving it geometrically or using calculus. Now, our kinetic energy. The way that we can actually derive an equation for this is going to depend on calculus, because we do not have a graph for force versus displacement when we're looking for a relationship to determine the kinetic energy. So we're going to have to approach this entirely using integrals. Our kinetic energy would be equal to the integral of our force acting on the system that's causing the displacement dx. So our energy is the integral of f dot dr. And then specifically, once again, I'm going to be focusing on our x-axis acceleration here, which would be proportional to our x-axis displacement, which is why I'm using x instead of r for our position variable. We can use Newton's second law of motion, which is the sum of the force acting on a system is equal to the mass of the system times the acceleration of the system for force, which is why our EK is equal to the integral of ma dx. We can use our definition of acceleration, which is the slope of a velocity time graph, and substitute that in here. Acceleration is equal to dv over dt. We can rearrange that, so that way instead of it's dv over dt times dx, we can do that our kinetic energy is equal to the integral of the mass times dx over dt times dv. Just rearranging this using the commutative properties of multiplication. Well, dx over dt, that's our definition of velocity. Velocity is the slope of a position time graph. So our integral is now the integral of mv dv, which if we solve that out, it's 1/2 mv squared. So our kinetic energy of our system is equal to 1/2 times the mass times the velocity squared. Now for our gravitational potential energy. Our force of gravity remains relatively constant, particularly when we are near the surface of the Earth. Regardless of what the height of the object is, it doesn't matter if it's displaced 1 centimeter, 1 meter, or 100 meters, or even further up. The change in the force of gravity would be negligible, so we can essentially see this perfectly horizontal line for our force of gravity versus the horizontal position graph, which would be the height here. So we can solve for this using geometry or calculus. The geometric approach is the area of a rectangle. The base here would actually be the height, and the height would actually be the force of gravity. The way that we solve for the force of gravity near the surface of the Earth is going to be by taking the mass and multiplying by the gravitational acceleration. So our EG is equal to mgh. We can do the exact same thing using calculus. Our gravitational potential energy would be equal to the integral of Fg dh. Once again, Fg is equal to mg dh. We can take out those two constants, the mass and the gravitational acceleration. So when we integrate 1 dh, we end up with just h. So once again, our equation for gravitational potential energy is equal to mass times the gravitational acceleration times the height. So once again, let's return to our definition of energy. Energy is the integral of f dot dr. Energy is the area under a force versus displacement graph. And a lot of times when you see distance, like here, that's just referring to a distance from 0, but it can also be rewritten as displacement. The equations that we have from this definition is work. Work is equal to F sub x times x. Our kinetic energy is equal to 1/2 times our mass times our velocity squared. Our gravitational potential energy is equal to mass times our gravitational field strength times our height. And our elastic energy is equal to 1/2 times our spring constant times the displacement squared.